Welcome back. We are now ready to define the matrix of a linear transformation on any vector spaces, or between any vector spaces, as long as they're finite dimensional. So let V and W be finite dimensional vector spaces with bases BV and BW. So to obtain a matrix, you need to pick a basis for the domain and a basis for the codomain. All right, so let T be a linear transformation. Consider the following diagram. All right, so I have my map T here from V to W. Having picked a basis for V gives me an isomorphism here between V and R. That means I can go this way and I can go that way. So I choose to go this way. So from Rn to V, that's the linear combination map. So L of BV. Having chosen a basis for W, I have an isomorphism between W and Rm. So I have one that way and one that way. I'm going to use the one going down. And so that's the coordinate map for BW. Right? So if I start here, I can take LB, I can take T, and I can get W. This composition is a linear map because all maps are linear from Rn to Rm, right? So that linear map is what you'll use to, let me write it. So we have a linear map here. That linear map we'll call T, BV, BW. All right, so let's look at this definition. Definition 2.4.1, matrix of a linear transformation. For any linear map T from V to W and any bases BV and BW for V and W, let T be V BW. It sounds complicated, but we need to give you the linear map. We need to give you the two bases. All right, so that's going to be the composition. I'm going to start with LBV, then T, then the coordinate map away from W into Rm. All right, so LBV, T, CBW. All right, and I'm going to take T, BVBW to be the corresponding matrix. I have a linear map in Euclidean space now. Using these identification, I've managed to go from a map between two different vector spaces, unknown, to two very well-known vector spaces, En and Em. We have a matrix for that one. All right, so when W is equal to V and we use the same bases, we don't need to keep both bases. We could just put TBV and the matrix of TBV. All right, so let's try an example. This is a bit confusing at first, I find. All right, let's consider the map between P2 and P3. Oh, sorry. uh, this bases, we need them here as well. So for B2, which is 1x squared, and B3, which is 1x squared x cubed. All right, so consider the map that from P2 to B3, that sends a polynomial to x times the polynomial. All right, so I want to give TB2, B3 of ABC. All right, so let's see. I'm going to start in R3. I have ABC. And the first thing I'll do is I'm going to use the linear combination map for this basis here. All right, so that's going to lend me in P2. I'm going to take ABC and I'm going to get A times 1 plus B times X plus C times X squared. Right, that's what the linear combination map does. You take 1x squared and you multiply them by the vector. All right, next step. Right, so we went from here to here. Now I'm going to apply T. T just multiplies it by X. That's going to land me in P3. So I'm multiplying everything by x, so I get ax plus bx squared plus cx cubed. And now I'm going to take the coordinate map back to back to Euclidean space, but now R4. So, I mean, the way it's written is already a linear combination. I just don't need any 1. And so the first coordinate is 0 because I'm not using 1. Then the coefficient of x is a, coefficient of x squared is b, coefficient of x cubed is c. All right, so we went from a pretty natural linear transformation on polynomial to this linear transformation on Euclidean space. All right, now I want to find the basis of that linear transformation. So I'm going to see what happens to E1. All right, so that's TB2. I'm going to actually spell it out. Yeah, let's spell it out. I think it's going to be helpful. So I'm going to follow exactly the same path from R3 to P2 to P3 and to R4. It's going to tell us how to do it in general, so I like it. I'm going to take E1, which was 1, 0, 0. All right, so when you go from E1 and you apply LB2, you're going to get 1 times the first basis vector, and that's it. So E1 is always going to be sent to the first basis vector here, and then you're going to apply T to it, and we're going to get X. And then here you have to use the coordinates of X, and so you have to write X as a linear combination of the basis for the codomain. In this case, it's not too hard. It's 0, 1, 0, 0. All right, let's start with E2. That would be 0 times 1, 1 times x, 0 times x squared, so that's just x. All right, again, second basis vector. Then you apply the map, which multiplies by x, and then you write it as a linear combination of this. You don't need anything but x squared, so 0, 0, 1, 0. We need E3. That's going to look at the third. Every time I say third, I write 3. The third basis vector, which is x squared. Again, multiply it by x. I get x cubed, and then transform it into a vector. Linear combination, don't need that one, don't need that one, don't need that one. Need one of that one, so 0, 0, 0, 1. All right, so T, B2, B3 would be, all right, so you apply the map to E1. That's going to be the first one. You apply the map to E2. That would be the second. And you apply the map to E3. That would be the third. And so you're getting 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. All right, so I want to learn something from this. I want to write out exactly what's going on here, right? When you apply, actually, let me shrink this a bit. You can write it. When you apply TBVBW to EI, that's going to first apply LBV to it. And LBV of EI, that's just 1 times the ith vector. So it's going to be VI, and you apply t to it, and then you have to write it in as a linear combination of the vectors in the basis for W, and so we have some notation for it. It's a lot to take in. There's a lot of notation here. So you take the ith basis vector, you apply your linear transformation to it, and then you write it in terms of the basis of W. All right, that's what the ith column of the matrix will look like. All right, so let's write that down. All right, it's a takeaway. If this is your basis, then the matrix of your linear transformation, according to that basis, is going to be, you're going to take t of the first. Oh, sorry, I put arrows here, but we don't need them. T of the first, and you write it in terms of the basis of the codomain. Same thing here, and you keep going. All right, so we'll do an example with that in the next video.